So, I didn't bring it to an introduction. I can introduce myself if you want. Good afternoon, everyone. So I'm sorry, I have to apologize. No problem, no problem. Okay, so good afternoon and welcome to On Straight Lines and our machine learning excludes them. Right? It's a bit of a pun, obviously. There's layers here, and I think the meaning will become more clear later on. So that's me, Yvan Dubois. I'm one of Professor Penne's students. I'm an engineer, an electronics engineer. And a few years ago, I became a lecturer at University College, where we were shortly colleagues. And then the engineering students moved to the University of Antwerp, and I stayed behind. But I guess we missed each other so much that we got reacquainted, and now I'm doing a PhD under the wing of Professor Penne. We are both with the INVILA, Industrial Vision group of the University of Antwerp. Okay? So, do I understand correctly that all of you are engineering students or in the field of engineering? Is anybody doing something else than engineering?
I don't think so.
No? Okay. Are you all doing robotics and computer vision? Stuff like that? Yeah? So, do you all use machine learning one way or another? Yeah? Who in you here uses machine learning but not a neural net? No one? Okay. Who in here uses devices that on one way or another rely on straight lines? Who in here? No one. Who in here has a device in their pocket that heavily relies on your cell phone, right? Okay. So today I'm going to revisit some of the topics Professor Penne explained yesterday, but more from a practical point of view. Okay. I'm going to do it really, really hand wavy. Now, if you want to do proper research, you're going to have to do proper math, right? Nothing wrong with that. Not at all. But for today, I'm just going to have it a bit light and breezy. But some of the concepts are a little bit abstract. If at any point I lose you, please interrupt me and ask questions. I don't mind this turning into a dialogue instead of a monologue. Okay? So I'm first going to present you with a few examples of applications where straight lines are really, really important. Then I'm going to introduce some mathematical concepts, just a smidge, and then I'm going to make a bridge to machine learning and talk about the challenges we have been faced with when we were working on these applications. Because predicting a number with machine learning, that's one thing, but predicting a line, that's something else. And perhaps you have similar challenges, maybe not the same, but maybe another context or something, and I'm hoping this would inspire you. Okay? So, first application, we have a robot arm. Where are the straight lines? Everywhere, right? Every segment of that robot arm, that's a straight line. So one of the segments traces out what is called a ruled surface. It's a surface and it contains only straight lines. Well, that's not right. All those lines together, they form a surface, right? It's a ruled surface. And a ruled surface is something, it's basically something you could do by taking an ordinary broom, a broomstick, and throw it around in the air. That surface, that's a ruled surface. It's a bit of an ugly surface because it intersects itself, right? It's a bit complicated, but it's definitely a ruled surface. Another example, a parallel manipulator, 6 pistons manipulating a hexagonal plateau, right? I know it's not used in practice like this, but it makes my point. So, where are the lines? Obviously, those 6 pistons. And there's a lot we can learn from those lines. But we will revisit these examples later on. This is kind of an obvious one. A LiDAR on top of a self-driving car. Each laser line is a straight line and it rotates around. Right? This is a little less obvious, at least it was for me a few years ago. I placed a camera in the scene and I'm making the camera zoom in and out. Where are the lines? I'm guessing some of you answered in Portuguese, but I didn't understand it, right? But every pixel is the result of one incoming ray of light. That's obviously a straight line. And by moving around this dot, we can zoom in and out. At least for a perfect pinhole camera. Okay? Good. And last but not least, the device Professor Penna was talking about yesterday. We have, let's call it a laser scanner. So we have one laser beam guided by 2 rotating mirrors. The lines are kind of obvious, but I'm going to visualize them now. They make this continuous net of what kind of shapes are those? Who remembers? So all the blue ones, or all the yellow ones, or all the red ones, what kind of shape is it? We had that thing yesterday with the wheel, we could rotate. It's a hyperboloid, right? Exactly. Okay. Now a little bit of math. How can we describe a straight line in our 3D world? Well, we could pick a point, the red dot over there, and a direction, right? And there are numerous alternatives you have to learn even in high school. Now, they all suffer from the same flaw. Maybe it's not a flaw, but something that's just isn't sitting right with most mathematicians, and that's the arbitrariness of picking that point. Right? You pick another point, you get another description for the same thing. It doesn't feel right. So it was the insight of this character, Julius Flügger, who said, I'm going to get rid of that arbitrariness, and I'm going to take 2 points. The difference is the direction again, and now I'm going to calculate a moment around the origin. And the moment is just what you think it is, like in physics. Imagine that straight line being a rope, and you pull it, right? Then you would get an infinitesimal rotation around the origin, which you can repeat with your right hand by going like that, and then your thumb is the movement. Okay? So we end up with 2 vectors, 2 3 vectors, 1 direction and 1 moment, 6 numbers in total. But as Professor Penna already explained yesterday, those are homogeneous coordinates, so in fact, these 6 tuples are points in 5-dimensional projective space. Yeah? Okay. This one was then later generalized by Krasman who, I think he defined it, the Grassmannians, that GR13 thing at the top reads as the one-dimensional linear subspaces of a three-dimensional vector world. Yeah, and you could use other numbers, so you could have flat two planes in a 20-dimensional world, right? You can use a similar reasoning to get to those two arguments. Now, some of you might be thinking, wait a minute, 6 numbers for something as simple as a straight line, that seems like an awful lot. In fact, it's too much. How many degrees of freedom does a straight line have in 3D world? 4, right? Because if you have a straight line, imagine my finger in a straight line, I can go like this, left, right, up, down, but I can't go back and forth because it's the same line. Same with rotation, I can rotate like this, like that, but not like that because it's still the same line. So I only have 4 degrees of freedom. Now we already lose 1 degree of freedom because they have homogeneous coordinates. Where do I lose the other degree of freedom? I'm sorry? I don't hear very well, so you're going to have to yell it.
That's the line topic to be another representation, right?
Yes, but that's rather technical. You are absolutely right, right? I was thinking of another phrasing. By construction, the direction at the moment to the orthogonal. Exactly, and that's what you meant, of course. Huh? Okay. So the direction at the moment, they are orthogonal to each other. And I've rewritten this 4 times. These 4 equations, they say the same thing. It's a really, really important property of a straight line, and it's so important that it has its own name, the Grassmann-Brugger relationship. It's also important for my talk of today, so try to remember that line. The direction and the moment, they are orthogonal to each other. So, we can do the math, and we can come up with this formula, right? Now, to the inside of this gentleman, Felix Klein, we said, wait a minute, that thing, that's the equation of a surface in P5. In fact, it's a surface of dimension 4 in degree 2. Surfaces of degree 2, they have a name, they're called quadrics. In a plane, they are conics, like a parabola, hyperbola, ellipse, circle. Yeah? So in higher dimensions, they're called quadrics. So all points fulfill this Grassmann-Brugger relationship, which means, all straight lines fulfill this Grassmann-Brugger relationship, which means that all straight lines are points that live on what is called the Klein quadric. I've drawn a quadric here. I cannot draw a 4-dimensional surface of degree 2 in 5-dimensional projective space on this board. Right? So I've drawn analogy, and that's green. It's also quadric. So that green dot there, it's a line in our 3D world. Is this making any sense to you? Okay. Now we can ask ourselves the question, are all 6 tuples automatically straight lines? Of course not, they have to fulfill the Grassmann-Brugger relationship. If they don't, we can still calculate that dot product, but in the general case, we're going to end up with a number that's called P, and P stands for pitch. So a general 6 tuple is not a line, it's something else, and we call that thing a screw. And it's that yellow dot you see over there. To visualize such a screw, it's a little bit tricky, but I'm going to try to do it anyway. Yeah? I'm going to define now something new, a linear line complex. Now, a complex in math is just a bunch of things, right? In this case, it's lines. And there's an equation for this thing, and that equation is linear. It's this equation. The equation is not important for today, but just know that it exists a linear equation. If I plug in a line, the white thing, let's call it L, this equation holds. If this equation holds, that line is part of the linear line complex defined by 2 given 3 vectors. Okay? point, you probably have no idea how a linear line complex looks like in our 3D world, but I will try to explain it now. I've repeated the equation over there. Imagine every point in our 3D world doing this rotation around a central line. I only drew one point, obviously, but imagine every point in our world doing this. These points all trace out a circle. Yeah? That circle is a path. Now take all lines normal to that path. So all points orthogonal to that path is the green ones. All those green lines will intersect this yellow line. Yeah? Is everybody seeing this? Yeah? Okay. So we can say now that all these green lines fulfill that equation. Trust me, they do. So all these green lines lie on a linear line complex defined by 6 numbers, and these 6 numbers in this case is a straight line. Pitch 0. Yeah? Now I'm going to add some pitch. Just a little bit. And now we see that every point in our 3D space is no longer rotating, but doing a rotation and a translation. Not just one point, all points. All those paths, every line perpendicular to that path, those are the green ones. They now are part of the linear line complex defined by the screw with a pitch of 0.2. Now we can easily expand the pitch even some more, not that hard to see. And in the limit, if your pitch is infinite, you just have translations. Okay? I know this is not very intuitive, and I swept a lot of mathematics under the rug, right? This is a course on its own. In fact, this field is called screw theory because screws are really central here. My only takeaway from this slide now is that the world of kinematics, where stuff moves, and the world of line geometry, they speak the same language. So if you want to be really good at kinematics, taking a look at line geometry might be worthwhile. That's my point here. Are there any questions up until this point? Yes? Oh, sorry, I clicked this by accident.
Curious, so I never read about this interpretation of the bridge. How does this connect with the representation of rigid motion with Lie algebras and by screws and so forth?
Yes.
This connects directly, interpretation?
If you're looking for an expert,
okay.
On straight lines and
yes, but so as a matter of fact, this screw can be considered as a center of motion, and if you want to do the transformation to the Lie algebras, we have this composition of rotation and translation. Asymmetric matrix is given by 3 elements, 3 by 3 elements. That's the first. That's the C1, 2, 3. These 3 first elements they are asymmetric, and the other 3 the transformation.
It's interesting. I never studied the two together in the same framework. So I studied a bit of lines, studied a bit of the algebra, but it's true. So for instance, the exponential, it's kind of a Blocker matrix. When you do the exponential with the screw, it's the format of a Blocker matrix. So there is a relation. So this relates with Schaaf's theorems and all that.
Yes.
Okay, good. Now that I have everybody excited about line geometry, let's play a little game. I'm going to show you some lines in our 3D world, and you are going to tell me, or try to tell me, how it will look like in 5-dimensional projective space. Okay? So we already covered a line. What does a line look like in P5?
Just 1 point.
Just 1 point, okay? And look what I can do. I can turn on my Gerastan-Flutter Kleinovision to visualize this line. It's just 1 point on the Klein quadrant, okay? Now, how about a flat pencil of lines? So all these lines go to one central point and they all lie in a plane, just 2D flat plane. How many lines do you need to define such a thing? Two lines, two lines. So what do you get in P5, or what can you define if you only have 2 points?
Curve. Geodesic problem.
Yeah.
No, you line complex.
It's easier than
Linear
that.
substance.
Yes. So a line. Okay. So all these lines are points that lie on a line in P5, and this entire line lies in the line. Is everybody seeing this? Okay. A little bit harder now. A star.
So this also happens if it's kind of 2 lines that are skewed, right?
Yes.
It's also a line space.
Yeah, and then the line is not on the line.
Right? So you have that kind of cameras, the cross-link camera and stuff.
Yes.
Okay. How about the star? All lines intersect in a single point, but coming from all directions. How many lines do you need to define such a thing?
You need just intersection. So it's
but how would you make a new line based on those 3? Let's say it like that.
3.
Yeah. So the thing you end up with is a plane, a flat plane, and that plane lies entirely on the Klein quadrant. I don't know how to draw that, right? But you can do it in 5-dimensional projective space. You just have to imagine this. This is the point where my analogy with the green thing fails, right? But just trust me that the white thing lies entirely on the green. The white thing is flat and the green thing not.
Maybe the interesting basic fact is if you have 2 points in projective space, in 5 space, and then if you take additions, the sums of these 2 points, you always come up with another point on that line, on the connecting line. Okay. Now, suppose you have 2 points there on the Klein quadrant. If you then have 2 lines, 2 corresponding lines, and you do the sums of those lines, then if they are not intersecting, you never come up with a new line and you have a screw. Just by the fact that every 2 lines are intersecting, means that the sum always gives a new line. So this means that every point on every point on the line connecting 2 points there is again on the Klein quadrant because it still is a line. So every of these 2 colored points, you can connect them and you are sure that you're on the Klein quadrant. And because it is true for all the points, all the colored points, because all the connecting lines are on the Klein quadrant, the whole plane is on it. So you can understand why it is, but you cannot visualize.
Yeah.
So the plane fits, the entire plane fits in the line. So any linear combination of 3 lines will be a line that belongs to the tensor.
The areas intersect, yes.
Because there are linear subspaces where this doesn't happen, right? Where you right or wrong. I'm asking. So if you define a linear subspace, a different linear subspace that it's defined by a number of lines.
Yes. In most cases, it's
not very far. Okay, so in this case, very far.
Yes, in most cases you can have, even if you have a line,
okay.
Most cases it's just going through the quadrant, so you have only 2 points of intersection, it's not continuous. If you have a plane, in most cases you have a conic intersection, but now, in this particular situation that you have this pairwise intersection of the line, so
any combination of
I have other examples to visualize what you were talking about. And I'm going to Screw them a little more. So a cone, part of a sphere, so it's now part of this plane. In fact, it's a curve of the Klein quadratic, and that curve is a conic. It's also degree 2. Yeah? And then the things you were talking about, what about the hyperboloid? Well, all those lines are points on the plane, but now that plane does not live on the Klein quadratic, it intersects it in the conic. That was what you were discussing. But see? I have some more examples. They increase in difficulty. This is a hyperbolic linear line congruence. I have two green lines, and then the congruence is the set of lines that connects these two. So for every point on this line, the green one, I connect it to all other points on that green line. These are all pencils, what we saw before. So on the line quadratic, they're all lines. In fact, all these red ones, they form a ruled surface on the Klein quadratic. So now things are starting to get really, really complicated, I know.
So that's only the space defined by dual strings, right?
I would say yes.
With a single string, which is different than to be generated than the number of lines that you need to move.
Yes.
And the two constraints or two degrees of freedom.
Yeah, that's okay, right? Because that's complementary.
So, but these codimension 2 is dimension 2, so it's a 4-dimensional subspace. It's a 2-dimensional subspace in the 4-dimensional.
And the last one, maybe it's not very visible, but these are all hyperboloids, and they're concentric, so they all have the same central point. They form an oval quadratic on the Klein quadratic. But this will become relevant later on. Now, let's revisit, now that we are a little smarter, those applications again. Here are my lines. How do these lines look like? What do they form on the Klein quadratic? It's a ruled surface, just like the cone, so we get a conic. Not a conic, not in this case, but a curve. The cone was a conic, but this is way more complicated than a cone, so it's a curve. Learn that curve and you know what your robot is doing, right? The same reasoning goes for the parallel manipulator. I have to turn my lines now. Like that. So every line is a point moving around on the Klein quadratic, and now you can study the constellation of those points. Because dangerous stuff can happen if two of those points coincide, or more of them become collinear or coplanar, stuff like that. I'm going to make an analogy again. Why do we drive our car like this? Because we have in our wrists, in our elbows, in our shoulders, a lot of freedom. Why don't we drive like this? Because now we are losing a lot of movement. In this position, my wrist cannot go directly to my shoulder. If I bend it, then my wrist can, right? So what's going on? If I put my arm like that, this line and this line coincide. It's the same line now. So these 2 points coincide. In fact, they are called singular positions, and they're really scary in robotics because they can break not only your planning algorithm, but even your device, right? Okay, these rotating laser lines, those are just conics on my Klein quadratic. The camera, a star. The lines back on again. A star is a plane, so if my lines change, my plane moves around on the Klein quadratic. And last but not least, what would this look like on the Klein quadratic? Just a bunch of hyperboloids. In fact, this is a big question because we don't know. This is still ongoing research, right? Now, Professor Penna has done already a lot of work on this, and he has formulas and stuff, and we talk about this thing a lot. But the actual visualization of a shape is a little trickier because I believe there are more possible shapes, depending on the relative orientation of the axis of rotation of the mirrors. It looks a lot like the hyperbolic, no, the elliptic linear line congruence, those hyperboloids that we're all considering, but that's not the case here because they move up and down on the second axis of rotation. See? So, in parallel to what Professor Penne is doing, the geometric algebra, I'm doing a machine learning alternative. So what we did in our work is we learned the map from two angles of rotation to a straight line. So we want to predict a straight line for any given pair of rotation angles. If you have that, you have calibrated your machine perfectly. Right? So I just use machine learning. Now, I don't use neural nets, I use something else. It's called the Gaussian process. Also a tricky concept to explain in just a few minutes, but I will give it a try. What if I give you a map of Portugal, and for 3 locations, you know the temperature, and I were to ask you, predict me the temperature in this beautiful city of Coimbra? Take a guess now. If this is I did this last week, and I thought this would be accurate temperatures, but it's way hotter here now, right? So take a guess. 24 degrees. Yeah. That's amazing. You only had 3 data points, and you could infer the temperature in the entire map, right? That's some. Yeah, of course. You're making assumptions. You're interpreting. What you probably did, without knowing that you did it, is you kind of put these 4 points, the 3 data points and the question mark, in one 4-dimensional Gaussian distribution. Yeah, you did. I cannot draw a Gaussian distribution in 4 dimensions, so I'm giving you an analogy again in 2 dimensions, right? But since we are in a Gaussian distribution, we can now just apply good old-fashioned statistics. We can calculate the value for the temperature at the question mark, given, that's what this vertical bar means, right? Those 3 points. That's kind of like the same in this 2D analogy. If I have the value of variable on this axis, what can I say about the other axis? And if I sample it, it will end up being something like that, right? So that's just a normal distribution. In fact, you could have said it's 24 degrees plus or minus 1 degree. That's something you kind of did in your head, and what happened here is things go vary, and that's also what's happening in the real world with temperature. If this one goes way up, they all go way up, right? That's a multivariate Gaussian distribution, but I can also do that in an infinite number of dimensions, an infinite number of question marks for every point on the map, right? Then my prediction would not be a value or a vector, but it would be a vector with an infinite number of values. So what is that? A vector with an infinite number of values? It's a function. Curve, right? So what you did, amazing, in your head, is you learned an entire curve for the map of Portugal only based on 3 points. It's pretty good, because they co-vary a lot, right? And luckily in our world, a lot of stuff co-varies a lot, especially here, 2 neighboring rotation angles will not end up with 2 completely different lines, and lines will be kind of similar. They co-vary. That's what I do. Why do I use Gaussian process instead of neural nets? Because you could also do it like that, just a simplification problem, right? Because now we can get away with fewer data points, which is an advantage in tedious work like calibration. Just a few points, and we can already map the entire thing. Plus, we also get an uncertainty, which allows various other theoretical things we can do. It's interpretable, it's not a black box. That's it. Is it kind of obvious? Or
what are the cons? What are the cons examples of using a Gaussian process instead of neural network. You are making stronger assumptions.
Yeah. The biggest con is that if you have a lot of data points, then they're really time consuming to train. In fact, it's big O notation n cubed. And that it just explodes. If you have more than 1,000, I don't know, 2,000 points, you're going to have to use some special trickery to get away with it. Right? So that's what we did. We wrote the paper about it, right? Using Gaussian processes to calibrate that thing over there. Now, a Plugger coordinate are 6 numbers. So what we did is we just implemented 6 Gaussian processes in parallel. That's what we did. What's the obvious flaw when doing that? Think about the title of the talk. Those 6 numbers from my prediction now, they are independent. So they don't necessarily fulfill the Grassmann-Plugger relationship. So I'm not predicting lines. What am I predicting?
Points.
And how are they called?
Lines. Just lines.
Screws, right? Screws. So we are predicting screws, not straight lines. So it kind of works, but things could be improved. So we wrote another paper.
What do you do? You project them at the end in the client quadrant?
That's what I thought, but Professor Penne convinced me of that it's not always that. No, because, and I'm really at the limit of what I understand about this now, but since it's not Euclidean space, you cannot. So it's a little bit more nuanced and complicated. Okay. So then the second thing we did is we observed that our outputs live on a manifold, Klein quadratic, but so do our inputs, because our inputs are angles of rotation. If you keep rotating, you're going to end up where you started again. So that's a circle, right? So what's the manifold you get if you have 2 circles? All possible pairs of rotations. It's not a sphere. I'm trying to trick you into saying sphere by doing so. It's a torus, also known as a donut, right? You have a circle, and then you have a circle, another circle, right? So it's a donut. So my inputs live on a donut, and my outputs live on the Klein quadratic. So these are constraints, and they're really hard constraints. They are quadratic, not linear, so it's kind of tricky. And it would be another talk to explain just how we did it, but we rewrote some stuff to make it linear again. Basically, it's really complicated. There was a lot of scary-looking formulas. It's maybe a talk for another day. But if you are working on a problem similar to this with constraints, you might want to look at this. Maybe not just for the stuff we did, but in the references, I have some really nice review papers done by other people.
So just to make sure, so basically, you are training the Gaussian process. First, you trained them independently, and you projected the results somehow. That was the first approach. The client logic to have a meaningful explanation.
More or less, yes. Yeah.
Right? And here you are trying to put the Grassmann-Plugger constraint, built in during the training process to make sure that you will have.
Under the hood, Gaussian processes rely on something called a kernel covariance function or a kernel. Those are synonyms, right? And you can make them really, really complicated and build in a lot of stuff so that the result of the predictions, they have to follow certain constraints, can't be any other way.
Okay.
But we need a lot more mathematical machinery to
sure. Just getting into it.
Just the kernel stuff,
right?
We made weak kernels, basically. Yeah. So, to wrap it up, we saw some applications with lines, with a little bit of line geometry, right? And I showed you what I did. I have more applications, but maybe that's a talk for another day. You have my name, you have You can Google me and you can contact me about whatever you want. I hope some of this stuff resonates and make you think about your own work. Thank you. And I welcome your questions, of course.
Okay, thank you.
Do you have another question? I think I cut you off.
No, let's hear. I think I've played the really good one.
So, yeah, there is no analytic way to impose the constraint, the quadratic constraint in the estimation process. So this is a quadratic constraint, and if you have models, analytic models for all these 6 functions, so we can insert these functions into this equation and derive probably some constraints between the elements of these functions. Am I thinking wrong? So you have a product of 3 elements or 3 functions that multiply each other, and they have to add up. That everything has to be equal to 0 is a very strong constraint. So if you plug in the functions themselves and then work on when is it feasible or?
Yeah, that's some of the stuff we played around in our first paper. So you don't need those 6 numbers. You can also work with 4 numbers.
Yeah,
you could intersect your line with 2 planes and then work with those 2D coordinates. Yeah, and then every prediction gives you 2D coordinates, and you just draw a new line. And the advantage is that that's a perfect line, which is 0, right? But you're kind of losing some flexibility of your model, and I think there is some trade-off there. You're basically making your model simpler, so it is not always best fit to learn complicated things. So we also added a lot of noise to our data, stuff like that. And then we saw that we could start to learn the wrong set of lines. Okay, they were perfect lines, which is great, which is 0. But if they're not the right lines, then it's a bit of a trade-off.
Yeah, I also think there is maybe this distance issue. Maybe I'm wrong because in this Gaussian process, you want to have this notion of distance. If your points in your input space are close to each other, their normal distributions should be very covariant, very impacted, influenced by each other. And if you have those 2 intersecting planes, then you can have 2 angles close to each other. One almost parallel, and the other also almost parallel to the plane, and with your intersection points, lines are far away from each other.
Then your problem might become ill conditioned, and then a small deviation in the angle gives you a point almost at infinity.
At infinity, but then maybe you can live with that, but then the fact that your distance is important in building your kernel. Distance is an important issue there. But another question should be, maybe there are applications that we do not have to care about having a screw or having a line. So maybe you train a Gaussian process, and this trained Gaussian process might deliver sometimes a line in pitch, so not a line anymore, the screw, but suppose then you have to hit this pseudo line, this screw with a plane, then you can still compute a point of intersection. So just the fact that it's not a line with a screw does not have to screw it up like that.
Yeah, all the formulas you use for lines still work with screws. It's a little bit trickier to interpret the results, but you still get numbers.
Yeah, so it's possible to neglect that.
No.
So can you just so you have the 6 function processes,
Yeah.
right? And how are you constraining the learning? So with these kernels. So
Yeah.
I think you were a bit describing the strategy that used to make sure that the output will fall in the line block.
Yeah.
Right. So what's more or less the mechanics that, in broad terms,
We did 2
the
things.
definition of the mechanics that you are using?
It's a little bit hard to get into without knowledge of kernels, but we did 2 things. We rewrote our kernel as a PDE. Differential equation, sorry. These differential equations are linear operators. And then there's a whole theory. If you apply linear operators on kernels, you're allowed to do it. You're going to end up with another valid kernel, right? But if your differential equation satisfies a certain constraint, then the kernel will end up, it also satisfies that constraint. So that's some of the stuff we did. And then we used this to enforce unit norm on the directions, because directions that have unit norm, those are just, they can be seen as points on a sphere. Yep. Right? So points on a sphere, they follow this linear differential equation. So if I apply this thing on my kernel, that looks pretty horrible, but okay, yeah, and then I end up with something that also follows that constraint. That's one approach, right? There are a ton of references where in physics constraint, machine learning, that kind of thing, a lot of examples about stuff like that. This is also given. And then the second thing we did is we rewrote the quadratic constraint again as a linear constraint, but with way more variables. So we don't have 6 of them, but how many were there? 21 now. So all cross products also.
So you lifted.
Sorry?
You use a lifting. You lifted it, you represented it in a higher.
Actually. So think of it like that. Yeah. So not only those 6, but all cross things also.
To get linear.
Yeah. Then you can apply the standard linear stuff. Yeah. But there's a major drawback because now your data set explodes, which was the drawback of a Gaussian process. So
you move the bad stuff.
There's getting rid of. There's a law in engineering. What's the law? Sorry, say it, please. Also that, but I was talking about the conservation of misery.
Yes.
Yeah. That's the law.
With these concepts, generally, because in broad terms you can move to the problem, and I'm not particularly familiar with Gaussian processes, right? But to these sort of problems, if you would use a neural network, it's about constraining the counter domain, right? And if you think in a neural network as an approximation of a function, because that's what you do, right? In trying to train a neural network, in a way that you are limiting the counter domain of what that neural network can provide. Right? So if you would use a neural network, you would want a counter domain that would always fall in the product of pi somehow. 2 questions. First, this approach would generalize, or your particular approach would generalize if I would use a neural network instead of Gaussian process, or if it's Gaussian process specific. And what do you know that exists in this problem of limiting the counter domain of a neural network? Because now that I did the thought, we have this in geometry a lot, right? Of representations that are subspaces, linear subspaces on a higher dimensional space.
I don't know how to limit the predictions of a neural net to a specific constraint. I think it's possible, but it's not my expertise. So I don't know, so I can't really answer that part of your question.
Okay.
But the thing that immediately popped into my head is all these lines, they're really tedious to measure. Because you have to move a board and then take the coordinates and stuff like that. So training a neural net, I would imagine,
Yeah.
you need a lot of lines.
I understand. I'm asking beyond your particular problem. It was
Okay,
understood.
yeah.
Beyond the problem, right? Because basically what you are using is that you are using means to somehow constrain the output of, let's say, a parallel Gaussian process, right?
Yeah.
Where each track is independent, and you are working to constrain them such that, as a whole, they have a certain meaning.
Yeah.
Right? Which, if I think in terms of a neural network where I would put out 6 parameters, which is an alternative way of trying to do this, let's talk it. For your application, I get the point.
Yeah.
It would be the smartest way. But okay, it would be the goal of limiting the counter domain of what this neural network is providing. I was curious to see if what you did could eventually be transposed for this problem of limiting the counter domain of the neural network, or if it's too specific to your problem in the Gaussian process. And use of Gaussian process. That's.
But all my magic is in how I defined new kernels. So if you have a method that doesn't use kernels, then you're losing that trickery. But I don't know enough about neural networks to say something smart now, but I think it can be done if you somehow incorporate it in a loss function, that if your output does not fulfill your constraint, you punish it somehow.
Yeah, because one way of trying to limit the counter domain would be probably train just with the elements of that counter domain in the output, but then it would depend if this counter domain was convex or not, it would depend on a lot of stuff. And then space of exit, right, the notion of the metrics that are being minimized will play a big role. But yeah, this would be an advanced version of doing this simple idea of just creating. I get your point.
But I'm certain that there exists a vast amount of literature on this problem, because constraints are everywhere. Sometimes it's not wrong to model people's height or weight with the Gaussian distribution, but somehow it's flawed because the Gaussian distribution goes from minus to plus infinity, and people's height and weight do not, right? So sometimes you only want to predict positive numbers, directions, so they have unit length. Constraints are everywhere, right? So surely the neural net community has come up with a lot of trickery to address this too. But if the kind of black boxy stuff, then I think there's a conflict of interest there. Okay, so thank you for your time. I hope it's late, and I hope you don't miss your bus or something. And again, if you need me, you know where to find me. Thank you.
Someone left taught this yesterday. Anyone? This is iPhone. Or then it's Apple. Yes. I don't know. Okay, thank you for attending. Okay. Yeah.
myself, so.
Yeah, yeah.
As
So,
well,
yeah.
I was elder student when I still had black hair. That's going to be.
Nice to meet you.
It was very interesting.
Thank you. You were the first ever. I've done this talk a few times before. That already did the client with. So, how do you do the client?
I've done a good deal of job, projected job.
Okay.
Right? Computer vision. And yes, I've worked with liftings, higher dimensional representations, so you can face it in a way as a lift, because I work with non-conventional sensors. So lift is kind of embeddings